Well, thank you very much. I shall now give a talk on smoking salmon, so, which I'll do as the postscript. It's a huge honour to have this prize. This may still be true, but when I was doing my PhD, people used to say there were two rites of passage for any experimental psychologist in this country. One was to pass your viva, but the real one was to give your first ever talk at the EPS. Particularly in the days when there was a certain selection of gentlemen who sat at the back giving you a really hard time. Time has moved on in maybe a slightly more positive way. Of course, there are many, many people who have been hugely influential. So many thanks to all of my mentors. I'm lucky to have more than one, including Carolyn and Jane McClelland and many other people. My brother over here. And all the people I've ever worked with, both directly as, collaborators, postdocs, students, collaborators, and many in this room, and also just for the sort of the rigor and scientific thought that I think is embodied by this society. Thinking about things carefully, how to do things properly, trying to be ambitious with our science. That's very much it's been steeped inside me. And I very much associate that with the EPS, other societies too, but certainly the EPS. And so to have this award is a really huge honour, and so many thanks. Given the time of year and having had a bit more thought about titles, this one is a sort of plain one. But I decided that as we're sort of not quite ending the festive period yet, we haven't got to 12 nights. So a different title for the talk will be Ghosts of Semantics Past, Semantics Present and Semantic Future. And some of that will resonate. I'm going to try to tell a bit of story about some of the things that we've been doing over the years, but also interweave that with some insights and thoughts about the past literature, going back in time quite some way. I just want to start by just sort of slightly self-indulgent couple of minutes just on things that affect the way I go about things. So ever since I was young, and I was weird, I was always interested in why people think what they think and how the brain might give us that, from being about 6 or 7. This meant I was more interested in listening to the adults talking to each other than playing with my cohort, which means you're seriously weird as a child. Because I thought it was really interesting about their interactions and then why they thought the things they did. So I was obviously a psychologist even then. For me, there are certain things that will come through hopefully in what I'm going to present, but I think they're sort of broader than just semantic memory and semantic cognition. So I thought it'd be useful just to lay them out. So cognitive activities or language activities really, I think we now know, really do not map in a simple one-to-one way to certain brain regions. It's sort of what we'd like. That would be easy if it was that the case. So if I'm doing, mental arithmetic, there'll be certain parts of the brain that does that, or that just doesn't seem to be the case. And I think that's one of the things that modern cognitive neuroscience has really taught us. Tasks really, and of course this will very much resonate with an EPS way of thinking of things, is a mixture of interactive cognitive components, or I like, because I'm very keen on cooking, to call them ingredients. When you're baking, or when you're making smoked salmon or whatever, you have to amalgamate all the right ingredients. And I think cognitive tasks and cognitive activities, you are doing kind of brain cooking. And I think it's more likely that ingredients are more likely to be localized. And actually what you're doing is you're orchestrating across the different storerooms of your brain kitchen and bringing those different things together. You wouldn't have all the things for making bread in the same place because some of them have to be in the fridge, otherwise they go off. You have to store them in the place that looks after that computation, but then you mix them together to do those activities. That's pretty much the way I think about things as a sort of starting point. So we know from imaging that you get a whole network and networks of areas. And I think there's going to be some challenges as we go forward in the future of thinking about what those networks really are, giving them a proper cognitive interpretation, which at the moment I don't think really happens. People just say, here's another network. I'm going to call it something with an abbreviation normally. The default mode network has no cognition in it. So that needs to come back at some point. But we definitely get multiple regions being activated. And I think there are two ways, and they're not mutually exclusive, that what that might reflect. It might be a mixing of core computational ingredients, and or there's a different way of thinking, which I sort of have inspiration. I'm not an engineer, but I think it's interesting to think about engineering sometimes. We might want to think a little bit about what's a well-engineered cognitive system. And I'm becoming more and more interested in how would you make something well-engineered, as in it would be resilient. It would be resilient to bits of damage. It could be the potential for recovery. And of course, I do a lot of work with patients, so this is very important. Where might you get some recovery of function from? And it may be because you've got a well-engineered system. If we were cognitive engineers, we would be stress testing all of our cognitive activities and tasks. And I think that's sort of an interesting thing we could think about in the future. And this ultimate goal in cognitive neuroscience of relating cognition to and from the brain, I actually think needs something to help us do the bridging. We are in the position now where we can measure cognitive behavior in a very sophisticated and detailed way. We can measure the brain in, terabytes worth of data, and we now have a problem with having too much data. But we still, I think, are needing a bit of a bridge to formally try and give you what cognitive neuroscience actually promises, which is hugely thrilling, but extremely difficult, which is to explain how the brain actually gives us the cognition, and when the brain goes wrong, what we see in the patients. And I think one route to there, to pick up on some of Tim Rogers' talks and Paul's talk from earlier, is we can use some of the computational models that give rise to behaviours, so something like the PDP models or anything that generates behaviour, and use anatomical constraints on it. That will start to allow us to have a bridge between the two things. So that's an overarching thing there. A few approaches, which I guess are associated with me and are very important to the way I do things. So a convergence of methods. Each of these has advantages and disadvantages. If you use one, you're very wise. You don't go mad, you don't go white-haired. But they all have these pluses and minuses, and by trying to amalgamate them, you can try and benefit mutually from what they're good at, and hopefully can reinforce where there's a weakness in another method. Sometimes you don't even know that there's a weakness in the method if you only stick at one method. It's the old, you can only search under the lit lamp issue. If you've got multiple lamps, you know that there was a bit. If you have a torch, you knew you had a shadow. But if you don't have a torch, you didn't know there was a shadow in the first place. And the computational modelling again. Very much, I am very influenced by what I see in the patients in the clinic. And that's often, for me, a starting point. And then go back into some basic science, and then use those findings and go back into the patient, sometimes a different patient group. And you can resolve things in a new patient group going through this cycle. And for me, it's very much forward and backwards translation. So patients and basic science and all the things that brings. And for very much for today's talk, I wanted to just, for me, the historical work is important, and I do try and read it and try and get back into it for multiple reasons. So one is, some ideas really stretch back a long time, even before computers, even things that are more than 2 years old. I think it's really important to see what those ideas were, where they came from. Sometimes those ideas have evolved over time, which is quite interesting. Sometimes, in fact, they haven't, which is also interesting. I think sometimes it's very easy to have a kind of filtering perspective on historical work, that we pick out the things that we like now. And so some of the ideas in the past, you think, that's amazing. Not very much data, fantastic thinking, weren't they smart? they didn't need brain imaging. There's a load of rubbish in there as well that we sort of don't, so it's quite interesting to know that from I think in our contemporary world, we're used to a mixture of good things and bad things. That's true in the older literature, and it's quite useful to see that. Likewise, there is a diversity of ideas. Sometimes we just sort of pick on one, but if you go back, people were arguing about things that are very similar to the arguments we're having now. I find it instructive to see that, and you'll see an example of that in a minute. The other is that contemporary summaries of work often don't bear a direct relationship to the actual work. And I'm going to try and give you a few examples of that as we go along today, sometimes even by the same person, which I'm going to give you an example of. So for me, trying to find the original work and trying to read through it, sometimes it's hard, like Stefano was talking about earlier, to understand really what people were talking about. All the vocabulary changes over time, so it's sometimes hard to know how to map it to a modern world. But I think it's worth a try. So, Ghosts of Semantics Past, Semantics Present, and Semantics Future. Here is a beautifully diverse set of people I'm going to talk about. A disadvantage of going into the historical literature. You'll see these people coming up as we go along. I'm going to start with some of the older work. So I feel, and especially as we're sort of in, not exactly pantomime, but I'm going to change dress to... I was born in the wrong century. Now, there's even a pocket in the back. It's very handy, so you can walk along like this. Now, this is not any old frock coat. This is my frock coat. I used to work for Coutts & Company nearly 30 years ago. What I'm most proud of is this is my frock coat, and 30 years later, I can still put it on. So I used to wear this every day during banking hours. It's extremely warm, which this time of year is quite nice. In the summer, it's terrible. You get this on your probation, only if you're a man. And then you take all of your department out for a drink in London. It's very, very expensive business. So, here we go, with frock coat. So here's some gentlemen that you probably know who they are. So the first bit is going to be about the relationship between sensation and semantics. And so we're sort of familiar with this under these sorts of terms like embodied semantics. So the semantics coming from our verbal and our sensory experience. And this traces back at least to, maybe before, to Maynard and Wernicke, who knew and understood that they were engrams or sources of information that arose in secondary association cortices near the sites where you perceive those in the brain, so auditory areas, visual areas, and so on. So conceptualization, as they called it, so making semantics, was the mass action of this distributed network of regions. And there's no localization of semantic representation here. It's a brain-wide activity. And so the only way you can break down semantics from a neurological point of view is to have a brain-wide disease. Okay, so this is what they believed at the time. This is probably still one of the most dominant ways of thinking about semantics. So we come through to Alan Allport's work. This is one of probably the first times I was really starting to think heavily about semantics, reading this. I really remember reading this paper. And it's very, very appealing, this idea. And you see versions of this all the way through into any form of relatively strong embodied semantic theories. And they're still here. So Friedman and Pulvermuller to a certain degree, and so on. And so for me, the positive features of this approach are that the sources of the ingredients for building the concepts are clear. They're not, if in other ways of thinking about things, how you even have some information to build a concept is mysterious. But in this one, it isn't mysterious, it's just your experience. So conceptualization, therefore, is a reflection of your multimodal experience, and this model can explain different forms of agnosia. So a problem in getting into meaning from any one of those particular input modalities. So that's all fine, that's very nice, very appealing. Certainly found that appealing as an undergraduate. But there are issues and challenges. So one are actually how are the concepts actually fabricated out of those. So we might have ingredients, but ingredients do not make the cake. You have to do some other stuff than just have the ingredients. And how do we explain multimodal semantic impairments from localized damage, which I'll come back to in a second. So, interestingly, not roughly at the same time, slightly later, Arnold Pick was describing a really sort of importantly in 1892, there's some debate about whether or not it was exactly semantic dementia, but somebody who was a bit like semantic dementia. The more important, whether or not it is semantic dementia sort of doesn't really matter. He was trying to say there is this focal neuropsychology in the context of a neurodegenerative disorder. So this is an example of contemporaries already disagreeing about semantics. Of course, the embodied one is better known, but Arnold Pick was already arguing, oh, hang on a minute, there's a focal neuropsychology here. Interestingly, this was very, very beautifully described in Japan by a very famous Japanese neurologist called Imura, who no one in the West has ever heard of. He's as famous as Henry Head in Japan, and is important. And his descriptions have everything about semantic dementia in them in the 30s. He even knew they were surface dyslexic. All the things we think of as a modern. And then, of course, Elizabeth Warrington, in the sort of modern Western literature, picked up and noticed the selective semantic impairment. And this is the disorder, for those who don't know about it. Carolyn already talked about it. So a multimodal semantic impairment, profound anomia, but then in the context of very good other aspects of language and nonverbal reasoning and other forms of higher cognition. And it's associated with atrophy bilaterally of the anterior temporal lobe, and including the ventral surface in plenty, including the pole, but also all this ventral surface. And you can see this knife edge atrophy, which is associated with Pick's descriptions of the cases. And if you do a glucose PET analysis, there's hypermetabolism in the same areas as the atrophy. So it seems like, really, the anterior temporal lobe and the semantic loss, you're getting a relatively focal, localized neuropsychological pattern here. So not what Maynard and Wernicke were going to be expecting. So over the years we've tested, they have a selective semantic impairment. All of these domains, every domain is affected. So understanding pictures, words, sounds, smells, tactile recognition and taste. They can do the lower perception, but they can't generate the meaning properly from them. They're affected both receptively and expressively, but there's this very structured breakdown of concepts. They're not deleted, but they become more and more fuzzy as the disease progresses. So we and others use this to argue that the bilateral anterior temporal lobes is the basis for a modality invariant contribution to coherent semantic representations. So here we are with Tim's seminal original hub and spoke model. So like the original distributed only models, information arises in certain association regions, so maybe praxis and vision and sound and what have you, but they all get interwoven together, and that's a very complex interrelationship through a shared representational hub, and the hub is in the anterior temporal lobe. That's the hypothesis. And as an advert, Becky Jackson, a previous EPS prize person herself, is going to do a lovely talk tomorrow about what happens if you wire this model in a different way. This was one that we particularly chose at the time, but there's lots of different choices. It turns out this is quite a good choice. There's others that are even better, but you need a hub. Okay, Why do you need a hub? Well, if you just go by kind of low-level similarities, you cannot build a concept very easily. So here's some mammals, and I've arranged them so they're visually similar in similar places. So the dark ones, the sandy ones, the striped ones, some weird ones. Okay, these are the cats. Okay, so the boundary of being a cat is extremely weird and non-linear. So there's a core area where these are fairly typical cats. Some of them are big, some of them are small. There's some really weird ones that don't have fur. And there's also some animals that are dogs that are pretending to be cats. And so to code this, if you think about this mathematically, to code this kind of boundary, you've got to do some very careful coding of the semantic knowledge, and you've got to break away from the surface similarity structure. It won't work, so you have to have some other representation. Jumping forward a bit to this chap, for me this resonates with some of what Wittgenstein was talking about in his last work, and this is a picture of him in 1950 in Cambridge. And so he emphasised lots of things that we resonate with now. So experience and use plays a key role in the making of concepts. Shared meaning is not always possible, though, by identifying a set of shared features, as in the sandy ones or the, whatever. And the exemplars can vary in form. So he used, this is in this time of steam engines. So all the handles in the engine driver's cabin, all what you call handles, are very, very dissimilar physically. Actually, they're all ultimately very different from each other. And then the more famous one, of course, is the game problem. He's setting out a chain problem and a closed series, but he's trying to use real examples. You also notice is that semantics is special because you can generalize your knowledge to a new exemplar you've never seen before. And in semantic dementia, they can't do that. That breaks down. Okay. And so, of course, here we are into family resemblances. And so this is his form one. So if you've got, these are each of the concepts, so these are the features in the concept. If these are all in the same category, you can't use the features anymore because there's no uniquely shared feature. But it turns out, of course, this is mathematically the same as an XOR problem or anything else where you have to do some nonlinear mapping, and you can solve this problem if you have another representational layer in the middle. So in an XOR, which is the simplest form of this problem, you can do the XOR learning if you have a hidden representation. The hidden representation is potentially the hub of the semantic hub and spoke model. So you need these spokes because they're the ingredients, but you need this extra computational resource to be able to build the concept. And that's important because there's all these non-regularities and all these kinds of issues that Wittgenstein and others pointed out. Smith talks about it in the 80s as well. Now, at the time when the sort of hub was being added to the theory, various people were surprised. This is dreadful business. Why on earth do we need this hub? This is complete nonsense. Alex Martin in the annual reviews of psychology said there's something really weird here, and he's correct. At the time, this is something weird if you're thinking about your contemporary literature. The ATL is not observed in endless fMRI studies of semantics of the time, and it's not in the classical neurological models of language. They have other brain regions. And we took that very seriously. And I'm going to show you bits of evidence that we've collected. So TMS, getting the fMRI sorted out, and some other neurological evidence. I'm going to do it with filtering back into the older literature. Maybe we didn't need to do all of that. Just go back into the older literature for some of it. So here's Henry Head and Rivers. If he looks pained, it's because Rivers is resecting his nerve in his arm. So one of the things I love about this time was people did experiments on themselves, which I consider to be a deeply honourable thing to do. If you're not willing to do the experiment yourself, then don't do the experiment. So 100 years later, this is not quite as bold and brave as those two chaps. Beth and Garana and I decided to experiment on ourselves with TMS. No one had ever done TMS on the anterior temporal lobe before. This is me having lost my wig in the MRI scanner. This is not some horrible disease. These are cod liver oil capsules stuck to my head, just so we knew where we are. So this is my whole scalp in the scanner, and we're using that to get to my brain. We stimulated my anterior temporal lobe. I was the first person maybe in the world to have this done to them. So not as brave as this chap, but you know. It makes your face really twitch. And especially if you do theta burst, it gets interesting. Anyway, so you can, the more serious point about this was we really want to be very careful about where we were aiming the TMS at. And if you do TMS, and you do a good job of your experimental psychology, so we're going to do left and right because it's bilateral according to semantic dementia. We're going to do a control task, which is a number judgment task, which is titrated to be as hard as the synonym judgment task. This is 1 Hertz for 10 minutes, so it's a virtual lesion or so-called virtual lesion method. And there's no effect on doing these number judgments. There's a 10% effect transiently for when you're doing semantics. And it's true on the left and it's true on the right. Okay, so there we are. And then with Richard Binney and other people, we sorted out some of the, or tried to at least minimize some of the fMRI problems. There's distortion problems and other technical problems in getting imaging working properly in the anterior temporal lobe. That's probably why it was missed. If you get things sorted out, when you do synonyms minus numbers, you now see the anterior temporal lobe, in particular this ventral part. Plus all the other areas like prefrontal cortex, posterior MTG that Beth and others were talking about earlier, and it's bilateral, although it's asymmetric because it's written words. So a nice coherent story from using the methods. So what about this additional neurological evidence? So there's Alex and others, Alex Martin pointed out it's not in the classical neurological models of language, which is true. It's worth knowing, though, that the classical models heavily, although not solely, are derived from post-stroke aphasia after MCA stroke. That's your sampling for building the models. The MCA supplies the superior parts of the anterior temporal lobe, but it doesn't supply further down. And the imaging and other things are suggesting that it's actually on the basal surface that's the most important part. That's outside of the MCA territory. You would never sample that with MCA stroke unless somebody had a very weird vascular setup. It's really in a watershed between the posterior cerebral artery and the middle cerebral artery. So what about those people? You'll see one of those later. Let's do some comparative neurology. So many of you will have heard of Kluver and Bucy, I'm sure. And of course, they're famous because there's the Kluver and Bucy syndrome, which is a neuropsychiatric disorder, or so you thought. Okay. And interestingly, the original studies, this was not pre-registered. Okay. If they pre-registered it, this was a study about understanding hallucinations and the effect of mescaline and other interesting drugs. And they were trying to test the hypothesis from Hewlings-Jackson that these aura and hallucinations were related to the uncinate fasciculus. And so that's why they decided to do some resecting the anterior temporal lobe in the primates and the monkeys. What they found was, a big surprise, was these rather wild monkeys were no longer wild. And so they had the Kluver and Bucy syndrome is psychic blindness, as it was called at the time, which probably translates to associative agnosia. It's often written up as visual associative agnosia. Hypermetamorphosis, which is an unbelievable desire to fiddle with everything that's put in front of you. You just want to explore everything and you're a bit obsessive compulsive about it. Changes in diet, eating a much broader range of things and having a go at things that are not edible. Increased oral tendencies, this is particularly in the primate, so exploring things in your mouth, and a loss of fear and sexual disinhibition. Some of these things will change over time. They showed that, here they are, Kluver and Bucy. But if you go back and read the actual original papers, there's some interesting things, particularly if any of you have ever seen a semantic dementia patient. So you go back to these papers, and it's not just a visual agnosia. So they do these anterior resections, and they say the fact these animals respond to yet do not seem to recognise the meanings of sounds suggests a positive agnosia in the auditory field. Tactile agnosia must also be considered. They had multimodal semantic impairment, in my view. They also had a complete failure to generate sounds, by which they mean conspecific calls to the other primates. They're anomic. Loss of fear and appetite, behavioural change. This is because they don't recognise the guards anymore. They're not fearful of the guards. They, before surgery, would go and hide in the corner, and afterwards they would just go up to the guards and engage and have cuddles and things. And they weren't worried about all the hooks and the things that were used to control them. So they lose that because they're not recognising what they are. And arguably, this difference between the food and the not food. This profound impairment requires bilateral ATR resection. So they do this beautiful surgery where they do it unilaterally, make sure the primates are not infected, they've survived their surgery, they're all well, they test them, wait until, and then they do the other side. And they also do some simultaneously. And they also do this amazing testing with the visual things. And at the end of the paper, they say many of these features are so interesting because they're the same ones that Arnold Pick has been describing in his patients. So they knew about each other's work. Some of this disappears out of the literature. To my huge surprise and horror, turns out this was actually done in a human person in the time of neuropsychiatric surgery. By Terzian and Delaore, a gentleman who had psychosis as a part of his epilepsy tried to murder one of his immediate family in an episode, and they'd read about this becoming calm after the surgery, so they gave him full-depth bilateral anterior temporal lobe resections. He became calm, he became completely asemantic, and the complete killer when you read the paper is his epilepsy comes back at the end. They knew about this. They cross-refer to Scoville and Milner's work and to HM and things. HM, of course, had a much more selective hippocampectomy. It wasn't full depth. And just to sort of show the link of to the modern world that people would know about. So Bucy was trained by Kluver, who then Pribram, and then to Mort Mishkin. And so Mort Mishkin and Pribram really went on and did more sophisticated selective surgery to try and unpick which bits of the anterior temporal lobe were important, and notice that the ventral areas were pretty important. What I like about this story is we all think, oh, that's a long time ago. In fact, they were not the first. It had been done 50 years before them in London by these two chaps. If you go further back in time, your pictures get even better. There's even cartoons of you. So Sanger Brown, who's a Canadian, and this fine gentleman, Edward Schaffer, who was based in London and went to Edinburgh and became knighted, a physiologist. They'd done the same thing on wild monkeys, very, very similar results, and also noticed that you needed bilateral resections. Here's a quick, I know I don't normally put quotes in, but it's so striking to anyone who's seen a semantic dementia patient. The remarkable change is, the distribution of the monkeys, prior to it, very wild and fierce. Now, after surgery, he voluntarily approaches all persons indifferentially, happy to be handled, teased, slapped, etc. His memory and intelligence seem deficient. He gives evidence of hearing, seeing, and of possession of his senses generally, but it is clear that he no longer clearly understands the meanings of sounds, sights, and other impressions that reach him. This is true for not just for inanimate objects, but also with persons and his fellow monkeys. So he's prosopagnosic, his agnosic and asemantic for all different categories, just like a semantic dementia patient. So it really fits. This story fits very nicely with the human neuropsychology. So semantic dementia, which is bilateral, you get this substantial semantic impairment, all these different domains affected. There's often behavioural change as well, which may be at least partly related to the loss of semantics. In unilateral resection, so things that we've done over the years and Grace and I have done more recently, you get a mild semantic impairment just like the primates do. So they noticed that although the primates don't have it floridly after unilateral, they're not as efficient and quick with meanings. Okay. So how do we want to think about a cognitive function that's split across two different brain regions? So the first reaction, and the normal one I get as questions is, well, what does the left do and what does the right do? With the implication they have to do something different. Of course, that's perfectly possible. So there could be two different functions that have to work together, or there's two different kinds of representations that are often being tapped by these tasks. And that I'm not discounting that as a possibility. There's another one, which is maybe that's a good way of building it from an engineering point of view. Maybe it becomes more resilient. And in fact, this is something that we did as an extension of Tim's model here. So Tim's model originally just had a single anterior temporal lobe, but we got two. So what Arne Shapiro did with Tim and Jay McClelland and I is took this model and split it. So you just have now, you have two demi-hubs. This is the demi-hub model. So in fact, it's exactly the same as the other one with actually slightly less connections because we stripped out some between the pseudo left and the pseudo right. Otherwise, it's trained exactly the same way. You turn on a certain input, it has to auto-complete all the other information, has to do it through now the left and the right. And they have reduced connectivity between them. And then you can try out in the model, which is very hard to do, of course, in human situations. What happens if you have bilateral damage versus unilateral, and also make sure you've controlled for total amount of damage, which is very difficult to do in the neuropsychology. It turns out, let's just do no recovery to start with. This is word to picture matching in the model, and this is naming. And these are when the damage is unilateral, and this is when it's bilateral. And at each point, it's matched for total damage. You can see in the model, like the humans, unilateral damage of the same amount is much less damaging to you semantically. And then if you allow a little bit of recovery, because obviously after surgery or whatever, you often have some degree of recovery, the models show some degree of recovery, but you still get this massive difference. So that retains, you just move the graphs up. And the reason, the nice thing about the models is, of course, you can explore why is that the case. And it's true for two reasons. One is you've got some redundancy of representation. But the other is that when you damage these models, not only do you weaken the representation, but you inject noise as a part of the damage. This is sort of you can't, that distributed form of representation, if you damage the bit of representation, you also make it noisier. The noise can propagate. If you keep all your damage in one place, and because of the restricted connectivity to the other side, you keep the noise in one side of the model. So you have a weaker but clearer signal out of the undamaged side that can drive the output correctly but more slowly. And that's what we find in the patients. They're slower, and unless you really require the full system, as in you make the semantic task hard, that's the only time you ever see the semantic impairment beyond timing. So just to finish off, we need to talk about this chap. So this is partly going back to Alex Martin's comment that it's not in the classical, the anterior temporal lobe is not in the classical models of language. So here's the classical model of language, or at least the one that Geschwind was very good at promoting. So it only has a dorsal pathway, for those who know about the dorsal pathway. And then you have, sometimes it's called Geschwind's area, but the angular gyrus, which has the meanings in it. So you have auditory and phonological input things here. It can go through the arcuate to the output to allow you to repeat. But also you can go off and activate the meanings, and the meanings can drive speech production. So everything's up here. None of it's down here. Okay. So I started digging around in here. Why did Geschwind not think the anterior temporal lobe was important? Was it because he just didn't see those patients? It's unclear. He probably did see progressive cases, but of course there was no imaging at the time. You wouldn't necessarily know where the damage was. Bruce Miller was very convinced he did see progressive aphasics, but we don't know. Dig around in these really famous, so the Brain papers, Scientific America and so on. He doesn't really talk about semantics very much in these, not that I can find. And when he does, he just says, oh yes, it's very important, the angular gyrus is the key area. And he thinks that's for two reasons. One is the angular gyrus is multimodally connected. You know, he knows his anatomy, that's of course true. You know, it's nicely positioned, you can pull all these different sensory things together. And he says something along the lines of, well, this is an obvious region for merging the information together into semantics, sounding a bit familiar. If I just replace that with the anterior temporal lobe, that would be my story. It's now the angular gyrus. And then he says, when it's lesioned, the angular gyrus generates a selective semantic impairment. He didn't quite use that term, without affecting other aspects of language. And so there's this paper. I think it's really worth, for those of you who don't know, this view is really, really influential. If you open any neurological textbook, this will be the story. And it's still the story, okay? And people, as soon as they get some activation in the angular gyrus, will say, oh, semantics. It's almost like an axiom. Okay, so it's time for the axe to come out, okay? Some alternative views going back in time. Here's a fine young version of Henry Head. This is what happens before you've done all that self-experimentation. Extremely dapper. There's a fantastic anecdote I'll just do very quickly about him. Apparently he's a great clinical teacher and he was doing the grand rounds across the road, probably looking a bit like this, okay? And he has his entourage and he's always correct. And so he's examining this young lady and he's listening to her heart, and she reaches forward, grabs hold of him and kisses him. And to his sadly male set of trainees, he says, gentlemen, typical gentleman. A man of self-confidence. He, of course, as Stefano was talking about, semantic aphasia damages probably those sorts of angular gyrus regions, as far as you can tell from missile wounds and other things over time. He said, well, it's not really, you do get a semantic problem, but it's not really the core semantics, it's all like making use of it, going beyond the meanings, as Stefano was talking about in his talk. So it's not really semantic representations per se, even if we think that's all right as evidence for the angular gyrus. This is young Wernicke. So Wernicke, as pointed out by Cornelius Weiler, actually had in his language model a ventral pathway. He considered that to be the dominant language pathway, and it was the one he thought was really important for proper semantically driven speech production. He considered the arcuate fasciculus just to be a set of fibers for doing auditory reflex, as in kind of echolalia. Now, of course, that's sort of debated, but I'm just trying to point out there were these other ideas around, for some reason, didn't get through into the Geschwind output. And then we've taken that in work, so Taiji Ueno and others, and Tim and others, we built a proper dual pathway model. This is a PDP model that's anatomically constrained. It does repetition, it does comprehension, it does speech production from semantics. It does a lot of this semantic speech production and understanding in the ventral pathway. It can repeat. If you damage this model in different parts, you get the different parts of aphasia, different types of aphasia. So it's just there to show that actually this has no angular gyrus in it. You know, so the anterior temporal lobe is the thing that's driving the semantics in this model. And this would take too long to go into, so just as a side note, contemporary studies of the angular gyrus implicate it in multiple non-semantic functions. So it's implicated in everything you can possibly think of. So theory of mind, as I've just seen Uta Frith in front of me, mathematics, episodic memory, bottom-up attention, you name it, it's involved. And Gina Humphries has done some beautiful work, this huge meta-analysis trying to unpick some of this, and some very nice, very elegant fMRI studies, which really suggests that, in my view, it has no major role in sort of core semantics. It might have a role in building up meanings or something over elements. That's still to be decided, but in terms of raw semantic representation, I think there's very little evidence, in my view, from fMRI for that. I know that that's a very controversial thing to say. Jeff Binder's not in the room, so I'm all right. We can talk about that later. So let's go and read, just to finish, let's go back and see actually what Geschwin's patient was really like. Slightly sad story. So it's a young lady, 22 years old. She had anoxia. She'd, for whatever reasons, left the gas heater on in the States. And was unconscious for about 17 days, I think it was. And when she came round, she had a complete transcortical sensory mixed aphasia, which means that, in her case, very pronounced, no evidence of comprehension of language at all. She had no propositional speech. She had an array of stereotypic phrases, though, and she would complete them. So she can complete famous phrases. She could learn new ones, interestingly. She was still singing familiar songs, and she learnt new songs. So some new learning, interestingly, here, but very in a just further sort of non-propositional form. She has preservation of repetition. All of her motor articulation was fine. She was very echolalic. 3 years later, following some surgery, she sadly died from sepsis, and meant that she went straight to post-mortem. I'm sure they had all the ethical approval for it. And it shows, as I'm going to show you in a minute, preservation of all of these core Sylvian language regions, including Broca's area, Wernicke's area, Heschel's, arcuate. So it gets called isolation of the speech area because that was a theory about transcortical sensory aphasia that Goldstein had put forward, and they were able to test it and support that hypothesis with this single case study. And they also, this lady still had good hippocampal and limbic regions, so I presume that helps with the new learning. Okay, let's actually have a look at her brain. So they did this beautiful piece of really detailed post-mortem with all slides and stainings, and it's all done beautifully. And so if you see grey sketched in, it means there's damage, and how black it is means how bad it is. Okay, so remember, this is Geschwin's key evidence. This is the paper he always cites. He doesn't seem to cite anything else. And here's the angular gyrus, and there is damage to the angular gyrus. And notice there isn't damage in all these perisylvian regions. So like Heschel's, posterior MTG, inferior supramarginal gyrus, all the frontal regions and some motor, it's all clear, all nice. And that's the isolation of the speech area. Okay, you can tell something's coming. So reread your own papers. Okay. So she has a load of rot in the middle and ventral anterior temporal lobe. Okay, it gets even better yet. Okay, it's bilateral. So they talk about it. One they say it's quite noticeable. It's so bilateral. Look at the ventral surface. There's huge rot. These are all the watershed regions. So watershed between MCA and PCA and also ACA. So she's got a full watershed lesion, which means that she's sadly ripped out basically all of her semantic network. Just to show you the direct comparison, Gina Humphries did a lovely study. We were looking at the comparison of the default mode network and the semantic network, but it meant that we combined data from 69 participants doing all sorts of different semantic tasks. Here is semantics minus active baseline in fMRI with distortion correction from 69 people, and look at the similarity. So this is a very active area in healthy subjects, as is the prefrontal cortex, as is the small posterior area, and all this ventral surface. So in what she's really done yes, she has damaged angular gyrus, but she's also knocked out pretty much every other semantic region in the brain. That's not remembered. And having got back to the anterior temporal lobe, it's time to end. Thank you very much.